lesson 3.4, where we discuss the inverse trigonometric functions. So we've had 3 lessons so far in trigonometry, and among other things, we discussed the trigonometric functions and their graphs. But in this lesson, we're really going to focus on discussing the inverse trigonometric functions for just 3 of the 6 trigonometric functions: sine inverse, cosine inverse, and tangent inverse. Let's recall, for the trigonometric functions, the domain or inputs, these are angles. And in calculus, or certainly in this ramp up, we measure angles in radians. Now, the range of a trigonometric function, well, the outputs say, I will just say it this way for the moment, these are the values of the trigonometric function. So for example, just as a comment, if you have sine or cosine, the range would be this closed -1 to 1. This we have discussed. If we have tangent, or in the other 3 trigonometric functions, it's different. But tangent, the range is -infinity to infinity. But what I'm trying to stress at the moment is we get values of the trigonometric function as the output. Now, in order to get an inverse trigonometric function, we interchange domain and range. You will study inverse functions more in general in calculus, or you might have before. There's something called an inverse function theorem for calculating the derivative of an inverse function. But we're really just focused on the inverse trig functions here, and we interchange domain and range. So what does that mean? For the inverse trigonometric functions, the domain, well, I'll just copy and paste. The domain will be values of the trigonometric function. So we are inputting, say, a value of cosine for a cosine inverse, or a value of sine for a sine inverse, or a value of tangent for a tangent inverse. And then the output, well, this will be an angle. So why do we need inverse trigonometric functions? Well, one example that comes up in multivariable calculus is, say you know the cosine of an angle, and you want to know what is the angle. Okay, we use that for finding the angle between 2 vectors. You will just evaluate a cosine inverse, for example. So, but it's an important caution. This bottom line on this page is, it's not quite so simple as exactly this, that we must restrict the domain of the trigonometric functions in order to define their inverses. And let me just mention this now with a picture so we can kind of understand why we must do this. Here is Desmos, and what I'd like to do, okay, we interchange domain and range. That means, say, if I wanted to talk about the cosine inverse, that would be saying x equals the cosine of y. Now, you see, if this is all I do, this is problematic because this is not a function. We discussed this early in the ramp up. This fails the vertical line test. Okay, if you take a vertical line between -1 and 1, it's going to hit the graph infinitely many times. Definitely not a function. Or if I said x is the sine of y, like this, you see it's the same problem. This fails the vertical line test, just exactly interchanging x and y in the graph. And we can also, before we go back to the slides, we can also look at x as the tangent of y. And you see now, well, this definitely fails the vertical line test. This would be just interchanging x and y. Problematic. And so we're going to have to restrict the domain of the sine, cosine, and tangent so that when we do interchange x and y, we actually have a function. Let's start with the inverse sine. I'll make this important comment. This is not 1 over sine. That's important to understand with all of the inverse trig functions. How we get this? Well, we need to restrict the domain of the sine such that When we flip along the line y equals x, or equivalently, we interchange x and y, passes the vertical line test. Now, looking at the graph of the sine, that would say it needs to have every horizontal line needs to intersect the graph no more than one time. And the convention is we restrict the domain of the sine to this closed interval from minus pi over 2 to pi over 2. Minus pi over 2 to pi over 2. And on the graph, we will get here, okay, so we can get minus 1 as a sine value. We will get all in here and then to here. So you see, by this restriction, we get the full range of the sine. It's just now this portion, if you flip along the line y equals x, it will pass the vertical line test. Namely, we will have a function. And so this is the definition of the sine inverse of x. It is the angle between minus pi over 2 and pi over 2, such that, let's see, maybe I should add theta. It's the angle theta between minus pi over 2 and pi over 2, such that the sine of theta equals x. You see, we are feeding in a value of the sine. We're feeding in a value of the sine. We are returning back an angle. This is how these inverse trig functions work. So the domain, well, the domain of this inverse sine, we're feeding in a value of sine. This is negative 1 to 1 closed. So that we can take in any possible value of sine here. And then the range, well, it's this, minus pi over 2 to pi over 2, also closed. So let's do some examples, just evaluating. This is what we want to get out of this lesson, have some understanding of what an inverse trig function is, and be able to evaluate some inverse trig functions. This is our goal. So maybe as we evaluate, let me draw a unit circle, because that will always help me think about trigonometry. You have to understand here, this is a value of a sine, a value of a sine, value of a sine, value of a sine. And then we're looking for an angle here between minus pi over 2 and pi over 2. So between minus pi over 2 and pi over 2 that has that value as a sine. The first example, sine inverse of 0. It says what angle between minus pi over 2 and pi over 2 has sine value 0. Well, the sine is the y coordinate on the unit circle, and the sine is 0 here at 0. The sine inverse of 0, this is 0. Sine inverse of minus 1, we're looking for an angle between minus pi over 2 and pi over 2, such that the sine of that angle is negative 1. And this is here, negative pi over 2. Next, we have sine inverse of square root 2 over 2. This is a sine value. We're looking for an angle between minus pi over 2 and pi over 2, such that the sine of that angle is square root 2 over 2. That happens here, pi over 4. And then finally, sine inverse of 1/2. We're looking for an angle between minus pi over 2 and pi over 2, such that the sine is 1/2. And this happens here, say, pi over 6. This is where the cosine is square root 3 over 2, and the sine is 1/2. So it's a few examples evaluating the sine inverse. Now let's move on to cosine inverse. But once again, I'm trying to make this remark for all the inverse trig functions we study. This is definitely not 1 over cosine. Let me add the word not. This is not this. Okay. So you see, looking at the graph of cosine, we have the same problem in that if you interchange x and y, or equivalently, you flip this graph along the line y equals x, this will fail vertical line test. But also, if we try to have the same convention of going from minus pi over 2 to pi over 2, as we did with the sine, that won't work because we would just have this part, which does not fill out the full range of the cosine. It also, if we interchange x and y, we would still fail the vertical line test. So the convention here with cosine is we restrict, I will shade it here and then write it on the next page, but we go from 0 to pi, this closed interval. And you can see looking at this that we fill out the full range of the cosine. And moreover, if we flip that sort of pink highlighted arc about the line y equals x, that will pass the vertical line test. So just as I shaded, the convention here is we restrict the domain of the cosine to 0 to pi. And this allows us to define this function. So let's write it out. Cosine inverse of x, this will be an angle theta. The x here, right? We have to remember this is a value of cosine. So this is an angle theta between 0 and pi, such that the cosine of theta equals x. This is the inverse cosine function. And the domain, just like with the sine inverse, the domain is -1 to 1. It fills out the full range of this cosine in this case. And the range of the cosine inverse is just 0 to pi. So let's do this example. Maybe I should sketch my unit circle here also, so we can think about the cosine as we solve this question. So here, just like before, in here, in here, in here, in here, it's a value of a trigonometric function. In this case, this is a value of a cosine. We want to give back the angle between 0 and pi. So this will be the angle between 0 and pi that has that value of cosine. First, cosine inverse of 0. What angle between 0 and pi has cosine equal to 0? Well, it's right here, pi over 2. So we get pi over 2. Cosine inverse of -1. What angle between 0 and pi has cosine equal to -1? Well, it's right here, pi. Cosine inverse of square root 2 over 2. What angle between 0 and pi has cosine equal to square root 2 over 2? And this will be here, pi over 4. And finally, cosine inverse of 1/2. What angle between 0 and pi has cosine equal to 1/2? Well, that would be up here, where cosine is 1/2, sine is square root 3 over 2. This happens at pi over 3. This is pi over 3. So there's were a few examples evaluating the cosine inverse. The last one we want to discuss is the tan inverse. This is a big one. In fact, I think in, say, calculus 2, this inverse trig function is the one that comes up the most. It's also my favorite inverse trig function, for the record. So what is the tan inverse? Well, it is definitely not 1 over the tangent. This is important to understand. This is not an exponent here. It's telling you a tan inverse as a function. So if we look at the graph, here's y equals the tangent of x. The question is, how do we restrict the domain such that when you flip what's left about the line y equals x, or interchange x and y, we pass the vertical line test? So I will highlight it, then we can write it below. The convention is just to use this piece. It's very similar to the restriction we did with sine, very similar. The convention is we restrict the domain of the tangent 2. Well, it's open here. Minus pi over 2 to pi over 2, open. You see, tangent is not defined at pi over 2. Tangent is sine over cosine. It's not defined where the cosine is 0. That's why all of these are places where the tangent is undefined. But we restrict to this open interval. Minus pi over 2 to pi over 2. We fill out the full range of the tangent. And then you see this pink shaded part. If you flip it along the line y equals x, we will have something that passes vertical line test. So let's write the definition. The definition. So x here is a value of tangent. Well, this is an angle theta. And I will say strictly between, because theta will never be minus pi over 2 or pi over 2. So strictly between minus pi over 2 and pi over 2, such that, well, the tangent of theta is x. The tangent of theta equals x. Now the domain of this, you see, it's the y values of the tangent, and that's everything. So the domain of the inverse tangent is minus infinity to infinity. It's one reason it's really important in a calculus 2 course, because it's the only one out of sine inverse, cosine inverse, and tan inverse that has domain all real numbers. Okay, and then its range would just be this open minus pi over 2 to pi over 2, like this. So let's evaluate the tan inverse at a few values just to practice. And then because this function is defined on all real numbers, I want to talk about the graph of the tan inverse. So as before, let's draw unit circles so we can think about what's happening. We have to remember tan inverse will just give us an angle here. So it's going to give us an angle between open minus pi over 2 and pi over 2. Let me also write this recall. This will help us in evaluating the tangent of theta. This is sine theta over cosine theta. This will help us. So let's do the first one, tan inverse of 0. Well, you have sine over cosine, and that equals 0, right? Because this is a value of tangent, value of tangent, value of tangent, and value of tangent. So sine over cosine equals 0. What that says is that the sine is 0. So what angle between minus pi over 2 and pi over 2 has the sine 0? Well, it's here. This is 0. Maybe I will do this one next because it will help us with this one. So tan inverse of 1. What does that say? So sine over cosine equals 1. And, well, we are between minus pi over 2 and pi over 2. Sine over cosine equals 1 says sine and cosine are equal. And that happens here. It happens at pi over 4. Now that we've thought about that, tan inverse of minus 1. Once again, this is sine over cosine. We want the angle between minus pi over 2 and pi over 2 such that sine divided by cosine is negative 1. Well, it says that sine and cosine are the same in absolute value, but have opposite SIGN. And so it would be down here. This would be negative pi over 4. And the last one, tan inverse of square root 3. Well, maybe I will write a little bit for this one. We know the sine theta over cosine theta is square root 3. And how can we get that out of thetas that we know? I'm going to make the one on top square root 3 over 2. I'll write this. So if we make the sine square root 3 over 2, and then the cosine would be 1/2. You see how the ratio, sine over cosine? We would have square root 3 over 2 over 1/2, invert and multiply. We would get exactly this. So this is the theta that will work. Now, has to be between minus pi over 2 and pi over 2. And so you see this happens, well, at pi over 3. So this was some practice evaluating. Now let's look at the graph of the tan inverse. Well, this is what we were looking at before. This is definitely not it. This would be if we did not restrict the domain. So let's X that, and then we can plot y equals we can do the tan inverse of x. And you see how beautiful this is and how it's exactly what we would expect it to be. We took this restricted domain tangent, and I will show you that again in the notes in just a moment. And then you flip it along the line y equals x. And we have this. So let's take a screenshot. And then we will put it in our notes. This is what we just saw in Desmos. But also, let me go back to here. You see, we just took this pink portion of the tangent, then we flip the graph along the line y equals x, or interchange x and y, and this is the graph that results. So this is the tan inverse. So let me just make a remark, and then this will be the end of this lesson. Well, what I want to observe here is as x grows without bound, this means x is getting larger and larger and larger. Okay, what happens to the tan inverse? Well, tan inverse of x approaches pi over 2. And this is something that you will study more in Calculus 1 and use, I would say, fairly often in Calculus 2. It's really saying something about a limit. But we see as x grows without bound, the function is approaching pi over 2. And similarly, you could make the remark that as x decreases without bound, the y value is approaching minus pi over 2. But I would just leave this one remark, which was an important one. So this is the end of lesson 3.4. Thank you so much.